record just for a bit. Okay. So, and let me bring this over to this side, data structures. All right, and then I made some corrections to stuff. So first off, I should have finished grading your quiz for that one that needed to be manually graded. I also added a quiz for recursion and the tree operations. The tree operations quiz. Let's see. So first off, let me go ahead and just see. That might be a bit too soon, but I was just busy setting stuff up yesterday. So recursion quiz, I didn't put a due date on it. Just have it done at some point. Let's see where we are in modules. So depending on where you are in your modules, right. So we've got maze solving, which was done yesterday, and then recursion. Yeah, that probably takes a bit longer than March 3rd is needed. So, because this is for module 7, sorry, for week 7. So yeah, totally. So let's go ahead and move that due date to pretty far away. Okay, next thing we need to do is specify when, that may be a bit too far in the future. Whatever, I'll fix it later. Recursion and then tree index tree. And I might want to alter the index tree assignment this semester as opposed to this one. I might switch this one up. Or I might do an easier and harder one. That's probably what I'm going to do. So I'll make this one this one's an easy one. Yeah, so assignments, boom. And then the recursion, I'll make due at the end of the weekend. No, publish it. Keep it. Now let me talk about the recursion quiz. The recursion assignment. The recursion assignment is one of my favorite ones because it is fun and we're actually dealing with puzzles, right? So for those of you who have not tried it yet, okay. This is the algorithm you will use. You will probably need to modify it depending on where you put this clear choices. You might need to move that around. But this is the generalized recursive backtracking algorithm. It is applicable to tons and tons and tons and tons of different problems. It, in fact, is applicable to the maze problem we just did, or that you should have hopefully completed. Right? This is actually the recursive version of that. But I digress. So what are your problems? First off, you get, again, a choice of one of two problems. You get to choose one of the two chess problems, and then you do Sudoku. So either chess problem you can do all three if you want, but you got to choose one of the chess problems. Okay. So the first problem is 8 queens problem, where basically put the queens on a chessboard in such a way that none of the queens can capture each other. If you don't know how to play chess, that's fine. All that means is that none of the queens can share a row, a column, or diagonal. Queens can move. The way queens work is that they move in any dimension. They can move in any number of dimensions, any number of spaces. So they can move in the rows, they can move in the columns, and then they can move in the diagonals. But it has to be the same amount. So if you're moving, so they have to do the diagonals, meaning they can't go, this queen on C4 can't go to E5 because you have to match the number of squares you move in each direction. So in a sense, it means rows, columns, diagonals. So the knight's tour simply says, here's the way a knight can move, right? They move in an abstract L shape, meaning that they move one square in they move 2 squares horizontally or vertically, and then 1 square in the axis did not move. So so this is the output of basically the different ways a knight moves. And I did this in LaTeX in like 20 minutes. It was very satisfying to come up with this. So your objective here is to do what's called a knight's tour, which is basically the knight moves to touches each square on the board exactly once. So basically just making sure that he moves in each square. Now you can start this knight anywhere you like. Your output should be either the chessboard. So you have two ways of doing it, which is you can list either, you can print out the chessboard and like have a visual representation of all the moves it made, or you can list the number of moves that the knight made in chess notation if you prefer. So anyway, this is one that's harder because the algorithm can take a bit longer. I suggest if you try this one, start it on like a 4x4 or 5x5. And then finally, regardless of which chess problem you choose, you need to do the Sudoku problem. Now, what is Sudoku? Sudoku is, now how many of you do not know what Sudoku is? It's okay if you don't. Okay, chat. Okay. You're going to be writing your own code here. All right. Sudoku. So chess, I've explained what you need to know for chess. For the 8 queens problem, it's just simply matching it up. Yeah, Sudoku's boxy number puzzle. All right. So let's go to the New York Times page. They do have a pretty decent, they have a nice Sudoku on thing. Okay. Although there are some other ones, but this one's easiest to find. So the way Sudoku works is that you are given a box filled with numbers. A completed Sudoku puzzle has every single row, column, and so a completed Sudoku puzzle has every row has the numbers 1 through 9. Every column has the numbers 1 through 9, and each of these 3x3 boxes has the numbers 1 through 9 in it. So here, for instance, we see that we have the numbers 1. We don't have 2. We have 3, 4, 5, 6, 7, 8. So we don't have 9 and 2 in this row over here. Everybody see the top row, how it's missing how it doesn't have 1 and 2 in it. Sorry, it doesn't have 2 and 9 in it. So let's think about where we can put it. So we need to put a 2 somewhere in this row. But we see that there's a 2 over here, right? So that means a 2 can't go over here or here, which means that the only place for the 2 to go is right here. Make sense to everybody? And since we've got all the numbers 1 through 8 over here, the 9 has to go here. So it's it's a logic puzzle. Okay. And then we know with this 3x3 box, we've got the numbers 1, 2, but not 3 in here. And putting a 3 here doesn't conflict with having a 3 in this 3x3 box, in this row, in this column, or in this row. Everybody following so far? Basically, you got to make sure that the columns have no repeats, the rows have no repeats, and the 3x3 puzzles and the 3x3 has no repeats. Make sense? Now, how in the world do you do a logic problem, right? And here it's basically, and here I can select this and say, hey, can you tell me where things should go? Or what the possibilities are, so I don't have to make some guesses. So obviously the computer could probably do this, with the logic, but that seems hard, right? Everybody agree that basically just trying to figure it out like this is pretty hard? Okay, so let's go to a hard puzzle for a second. So what we would, or actually a medium, because that will give me a better chance for this. All right. So let's think. So let me go ahead and show you the recursive backtracking method way of doing this. Now, the idea behind recursive backtracking is that it is a smart brute force. Okay. So what is a brute force solution? Anybody want to speak up on that one? What is a brute force solution?
You just try every possible solution and test to see if it's correct.
Right. However, every possible solution in this case would include things would include things like this, right? It would include things that are obviously incorrect, like putting all the ones in the top column, right? It would just try everything, right? So what a recursive backtracking does is that basically it trims off incorrect branches of that solution. So the way the recursive backtracking works in this case is I'll say, okay, I'd like to try putting a 1 here. Well, that won't work. So I'm going to try putting a 2 here. Okay, I put a 2 here. Let's move on to the next square. Oh, it's filled. Let's move on to the next square. Okay, let's try by putting a 1 here. That won't work. What about a 2? That won't work. What about a 3? Well, that won't work because we've got 1 in the same by 3. What about a 4? Let's keep, okay, that works. Let's keep going. 1, 2, 3. Okay, 3 will work there. 1, 2, oh, 1 will work there. 1, 2, 3, 4, 5. Oh, that won't work. 6, 7, 8, 9. Okay, 9 will work there. Okay. 1, 2, 3, 4, 5. Oh, 5 works there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Huh, notice I went through all the possibilities and it didn't work, right? So in this case, I backtrack, clear out that square, move back here and go on and continue going, right? This hit a dead end. So I can trim all those, so I can trim out all those possible permutations that are down here that would have started with this, this answer sequence, because once we get this far, we know that basically this sequence is invalid. So we don't need to try going on to any further squares. We know it's impossible. So that means that we need to backtrack. 6, that won't work. 7, 8, 9, that won't work. So now, whoops, hit page down rather than delete. Backtrack, backtrack. Oh, backtrack. 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now we're on to the next square, next row. And then we just keep going until we get to the end. Now, believe it or not, does this sound like a very logical way, very elegant way to solve a puzzle? No. Does it work? Yes, it works because it's very quick and because it's very quick and because it trims out all those extra combinations. It eliminates a lot of those 9 to the n empty squares permutations that Reed put in chat. So so this is really helpful or really a nice way of doing that. That being said, for those of you who are curious, this is an NP complete problem, just a small one though, so it doesn't take too much time to run. And if you're curious about NP complete problems and those kind of things, and what that means, then I highly recommend you watch one of the videos that I have in a playlist on my YouTube channel, which I use, and I use this feature a lot because, let's see. So I have a playlist on my YouTube channel called Worth Watching, which I find, which are things that I think that are worth your time to watch, but are not necessarily in the bounds of any of the classes I teach. So here, this explains the idea of P versus NP and the whole idea of computational complexity. This really goes into a deep dive in Big O. And since I don't do stop motion, I don't know how to do stop motion, this definitely has higher production values. This is a cool puzzle. This is pretty interesting. It's actually kind of amazing. This is also something that's quite amazing for people who are curious about game engines and stuff. But I have an entire playlist of stuff that's worth watching if you want to procrastinate on certain things. So, Tom Scott's great, right? So So if you, by the way, if you happen to find any YouTube videos that you think that are worth watching, or are applicable to the class to add to a playlist, I'd be more than happy to take suggestions. Okay, so okay. So you want to do one of those 2 puzzles. Oh, and there's extra credit, right? Worth 10 points. Solve Project Euler problem 96. So those of you who do not know, what is Project Euler? Project Euler is a website where you are basically asked to program in some math. It's basically a programming practice website / math practice website. Anyway, so one of the problems we have is problem 96 for Sudoku. Again, it just talks about, it gives you the rules for Sudoku again. So what they do is that they give you a 6 kilobyte text file that looks like this. Here's grid 1, and then zeros for the blank spaces. Here's grid 2. Here's grid 3, 4, 5, and all the way up through 50, right? So, and what they want you to do is that they want you to solve 50 Sudoku puzzles, okay? 50 of them. Okay, they want you basically solve them back to back to back. And what you want to do is by solving all, and they want you to verify it by adding together all the top 3-digit numbers over here. So for instance, this puzzle has a top 3-digit number of 483. So when you add them up together, you should get this number. That's going to be your verification that your correct answer is correct. That's how you prove that you solve 50 Sudoku puzzles with just a number. Okay, it is quite good. It's quite fun for those of you who really are like really crazily mathematically inclined and want to have fun with that. I also recommend problem 497 if you're really into statistics and stuff like that, which is Drunken Towers of Hanoi, which is yet another fun recursive puzzle, one that I would be very happy to do. I probably will do that in class on Wednesday. That's just a fun exercise once everybody's had the chance to check up on recursion. Okay. And this is basically a mathematician who knows how to play it perfectly, but he can't control where he moves. So tell me how many estimated number of moves does he have to make? It's quite an interesting puzzle. A lot of these early ones are really good though for learning how to do some programming things. For instance, this one doesn't, on its surface, isn't necessarily too hard. The idea isn't too hard, right? Work out the first 10 digits of the sum of the following 150-digit numbers. So just add these numbers together. But depending on the programming problem you have, right? Depending on the programming language you work in, how do you do that? Right? There's different ways to do that. And so here you add those together. So how do you add together giant numbers in Java? In Python, it's no problem. You just add them together and integers can be infinitely big. Another one, coin sums is a very good one, which is in the United Kingdom, here's the currency. How many ways can you make change for this amount? And so how do you solve these kind of problems? Now, yeah, while I do have the answers up here because I've solved this problem, I highly recommend doing them yourself because you'll be robbing yourself of a learning opportunity if you don't. Similarly, with these recursion puzzles, okay? Similarly with these things. The A-Queens problem and the Sudoku problem are very well known, are very, 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 very well known problems for homework. Right, or not necessarily for homework, but they're very well-known problems or exercises for teaching recursion. I highly recommend you try your best to do this and not look up any answers. If you get stuck, reach out to me, and I'll steer you into the right path. Okay. But if you try to look up the answers and modify answers from online, you're going to be robbing yourselves of a wonderful learning opportunity. These are really satisfying puzzles to solve. All right, that's what I got for you. So I'm going to go ahead and open up the breakout.